Hello everyone, welcome to today's video. Today we will be looking at the inverse trigonometric functions. So we'll start by recalling some information about inverse functions in general. Then we will carefully define the inverse sine, cosine, and tangent functions based on what we recall about inverse functions in general. Then we'll start composing trig functions with their own inverses. Sometimes there's a nice relationship there. We'll have to look at their domains to see if that happens or not. Then we'll look at composing trig functions with other inverse trig functions and trying to map things around that way. And then we'll finish off by looking at writing trigonometric expressions as algebraic expressions, which is a skill that often gets used in calculus. So let's hop into it here. We're going to start with this slide, which I just straight copied and pasted from our video on inverse functions as a way to remember some things about inverse functions in general, which will help us with these inverse trig functions. So we're letting f be a one-to-one function here, which means that for every value in the range, there is only one input that is being sent there. So that is what we need in order for a function to have an inverse. Here we have domain A and a range B, so I'll just start writing some stuff in here. We're looking at a domain of A and a range of B. And then we would say that its inverse function has a domain of B. So over here for f inverse, we would call this its domain. Oops, I can write that a little better. And we would call A its range. So they're just reversing roles here. And then we're defining it with this property that if we have some value over here in A called x, and f maps it over to y, then we would call y f of x, because these two values are connected with this relationship, or this function f. Since we have this inverse function, that means that we can also look at mapping y right back to x using the f inverse function here. So we would say that f inverse of y is equal to x. And this is what this very mathy notation is saying up here, that f inverse is equal to y if and only if f of x is equal to y. So we have f of x being equal to y. We have f inverse of y being equal to x. This is the relationship that we are claiming, so that these functions are inverses of each other. Okay, so let's look, where we want to look here, which is at trigonometric functions. So let's say that this f of x function here is the sine of x. So remember that when we are dealing with trig functions here, that what we're taking the trig function of, or the sine of in this case, would be some angle theta. So I can say that there's some angle theta over here. And so that means that everything in my oops, that doesn't say angles. This says angles, but everything over here in this set will be angles if we're either looking at it as the domain of f or the range of f inverse. But that's kind of the punchline here of what I'm trying to talk about, that we would take some angle and it would send it over here to some other value that is a ratio. Oops, it is a ratio. So that is what our f function, our sine function, is doing, is it's taking some angle theta and it's mapping it to some ratio in the range. But what we want to start looking at is trying to find some inverse function, so something that we could call the sine inverse of x, that would take our ratio and map it back to find this angle theta. And that will be a super important thing that we'll want to do. Sometimes we will know the relationship, the side lengths, but what we actually want to find is that angle that's creating that. So now we will have a way to do that by defining these inverse trig functions. So over here, I didn't finish writing it, but these are ratios over here. So depending on what we're looking at, if we're looking at just a straightforward trig function, we're sending angles to ratios. But when we're looking at the inverse trig functions, we're mapping the ratios back to angles. So keep that in mind as we start working on some of these exercises going forward. So just a little bit more about inverse functions here. I probably could have squeezed it on the last slide if we had room, but there wasn't. So at the top here is just that same relationship, that f inverse of y gets sent to x if and only if f of x gets sent to y. So here we have the sine of pi over 6 being equal to 1/2. So then if I want to find the sine inverse of 1/2, that's just going to send it right back where it started from, which was pi over 6. So there's nothing too crazy going on these slides here. Going forward, we might need to be a little bit more careful with what's going on. here we have the cosine of pi being mapped to -1. That is something that we know is true. So once we define the cosine inverse of -1, that would send it right back to pi, right back to where it started from. And then we've got the tangent the tangent of pi over 4. We know that that's equal to 1. So if I wanted to find the tangent inverse of 1, then that would map it right back to pi over 4. So just showing, illustrating this relationship of the input getting sent to the output, and then they can reverse roles where the output gets sent back to the input if we're viewing that as the inverse. A little looseness on the language there, but that's the idea. So now we need to be a little bit more careful with what we're doing. So we need to restrict these domains if we're going to be able to find inverses. So no periodic function like sine is 1-to-1, because each output in the range corresponds to at least one input every period. So here we can illustrate that happening by just using a vertical line, or I'm sorry, the horizontal line test. If I draw, that wasn't a great horizontal line, but I can try a little bit better. So there we go. There's a horizontal line, and we can see that this is failing the horizontal line test a lot. It's failing it infinitely many times, and we can see that within just one period, so one period going from like 0 to 2 pi, we can see, yeah, there's a couple values within each period that's going to fail this horizontal line test. So what we need to do is restrict our domain so that we can actually try to get an inverse function here. So we need to make a 1-to-1 function if we are able to get an inverse. So what we're going to do is just restrict this here. Let me change my pen size a little bit. We're going to restrict our domain from negative pi over 2 to pi over 2. So we could pick different inputs here that would accomplish the same goal, but this is kind of the nicest one. So what we see here is that we have all of the output values from -1 to +1, and we are now 1-to-1. So if we're just focused on the pink range here, we pass the horizontal line test. There's no spot on here where we hit it in more than one spot. So we are good here. We have accomplished our goals. We've got a 1-to-1 function now, and we're getting all of the output values. So this is where we will focus our attention. And notice that the range is just going from -1 to 1. So we will use this restricted domain of sine in order to define our sine inverse. And this will be a large consequence going forward, that we need to be careful about the domains and where we're looking at in order to get things to work out here. So the inverse sine function, also known as the arc sine, is denoted with this inverse notation of the -1. Remember, that doesn't mean to take a reciprocal like it does for fractions or for exponents, but this is talking about the inverse function. So what I'm trying to say is that sine inverse of x is not the same as 1 over sine of x. So be careful with that notation there. It's an easy one to make. We know what this is. This is the cosecant of, oops, forgot a letter there. This is the cosecant of x, and the cosecant is not the same as the inverse sine. They are there's a difference between reciprocal functions and inverse functions. So keep that in mind as well. An easy mistake to make. So we've got this inverse sine function, or the arc sine function is the inverse of the restricted sine function. So we need it to be restricted in order to have this 1-to-1 property between -pi/2 and pi/2. So here's our relationship, just like we saw it before, that if y is equal to the sine inverse of x, then the sine of y is equal to x. So the roles of the inputs and the outputs are just reversing for these here, just like they do for all inverse functions. And we've got them graphed here below. So in the red is the sine of x, and we can see from the red portion that this is going from -pi/2 to pi/2, which means that when we look at the inverse function, that means that the outputs now will be going from -pi/2 to pi/2. And if we want to take a look at the outputs for the sine function in red, then this is going from -1 to +1, which means that when we look at the inverse here, then these outputs are becoming inputs, and our inputs for the sine inverse are going from -1 to +1. So this is showing that the domain for the sine inverse is going to be from -1 to +1, and the range will be from -π/2 to π/2. We can see that on the graph here, and we can see this is just included so that we have some sort of frame of reference. Remember that inverse functions, their graphs are reflected over the origin, and this y/x is just giving us the reflection line through the origin here. So let's take a look at evaluating some things here, because we need to be careful that we are in our domain. So what this first one here is asking us to do is find the sine inverse of the -√3/2. So what the sine inverse is doing is it's finding an angle, some angle theta. So writing like this can be super helpful, especially when we're starting out. It's sometimes difficult to keep straight in our heads, like what we're looking for, what those objects are, if they're angles or ratios or what. But here the sine inverse is finding an angle. And so what I could do is look at taking the sine of both sides here. If I take the sine of this side and the sine of this side, then I will have that the -√3/2 is equal to the sine of theta. And what we're trying to do is find this angle theta. So I'm going to draw a picture. You will notice that in this section we'll be drawing lots of reference circles. Either, I should draw the circle first, since the computer does the circle for me. We'll be drawing lots of kind of reference, either unit circles or just circles. We won't think about them as unit circles, but they will still be helpful. So we're looking for where the sine is -√3/2. The -√3/2 is down here somewhere on the unit circle. And if I'm looking for a sine value, I know that we're only defined, let me maybe do this in a different color, that the outputs for the sine, or the restricted sine function, is just going from the -π/2 up to π/2. So what I'm thinking about is I'm just restricted to this right-hand side of the unit circle here. So keeping that in mind, what I want to do is find where the sine is -√3/2, which is going to be this angle here. And this angle here that we are creating is -π/3. So remember that our outputs here, the angle that we're finding needs to be part of our restricted domain for sine, which is going to be between -π/2 and π/2. So this is telling us that the angle theta that we have found is -π/3. So just using this picture here to get that. Next, we want to find the arcsine of 1/2. So we can do the same thing that we did before. What we're trying to do is find some angle theta. So what we can do is, to more explicitly see what it is that we're trying to find, is take the sine of both sides here. So that on the left-hand side, the sine and the arcsine are undoing each other, and we just have 1/2. And then this is equal to the sine of theta. So what we're trying to do is find some angle theta such that its sine is 1/2. So let's draw a quick reference circle over here. Again, we are looking at the arcsine, and the arcsine is only going to be defined for values, for output values over here, or where the sine lives over here. Looking at this, we want the sine to be 1/2. So +1/2 is here. And if I map this over, this is going to correspond to this angle here. And this angle is π/6. So that tells us that this angle theta that we are looking for is going to be π/6. The last one here is sine inverse of 2. And already maybe there are bells and alarms going off in our head because we are restricted to our domain here. And the domain for sine inverse says that this angle, I'm sorry, not the angle theta, but that x, the input here, needs to be in this interval from -1 to +1. And the input that we have here is not in that interval. 2 is not in this interval from -1 to +1. So there is no solution here. This does not exist. That's usually the way the homework systems want them, is does not exist, or whatever it says. But we could also, if we we're just kind of on autopilot. We went to check, okay, let me just draw a unit circle here, and I'm trying to find some angle theta that will give me a sine value of 2. Well, 2's like way up here, and we're never going to accomplish that goal because we're stuck on the unit circle. The highest that the sine ever gets is 1. We will never find an angle with a sine value of 2. So we get that there's no solution here. The angle does not exist. However, we're thinking about that. All right, let's take a look at the other inverse functions here. So we looked at sine before and we had to restrict that domain. We'll need to do the same thing with cosine. So you can see here we've got the full cosine function and it would fail the horizontal line test. So we're just going to restrict our domain. Instead of restricting it from negative pi over 2 to pi over 2, that would give us just this like little bump right here. And that would fail the horizontal line test. So we don't want to take the same restricted domain here. So we're going to shift it over pi over 2, which hopefully makes sense since the sine function and the cosine function, their graphs are just shifted by pi over 2. So that's what we're going to do here. And we're going to look at going from 0 to pi. And this will accomplish our same goal before where we're now 1 to 1 in this restricted domain. And we're hitting all of our output values from -1 to +1. And next to it here, we just have the graphs next to each other. So we've got this line going through the origin. This is just where we're reflecting each graph. So red corresponds to red here, that this restricted cosine is our restricted cosine over here. And then the yellow is the inverse. And we can see that the outputs here are going from 0 to pi because our restricted domain is going from 0 to pi, and we can see that the inputs are going from -1, so it's not listed here, but -1 should be about there, to +1 on this side here. So there is our inverse cosine restricted for these values, so a little bit different from sine, but we needed to make that shift over by pi over 2 to make sure that we were 1 to 1. And then here's just those relationships that we saw before, where x is getting sent to y and y is getting sent to x, just ensuring that these are inverse functions and just the different notations here. And then we'll do the same thing with the inverse tangent function. So the inverse tangent function, with all of its notation here, we also need to restrict this. So this is not a continuous function here, like the sine and the cosine are, but we still have repeating periods here, and we are failing the vertical line, or I'm sorry, the horizontal line test infinitely many times, just like we were with sine and cosine. So we need to restrict this as well. So our restriction here will be this red guy going from negative pi over 2 to pi over 2. And we will just focus on this period here. Notice that we are not including the endpoints here. So this is the same, almost the exact same domain as the restricted sine function. For the restricted sine function, we can include, where did it go? We can include the endpoints since, maybe here, we can include the endpoints since they exist for the sine function. So we can look at these values here. But we have vertical asymptotes for our tangent function at negative pi over 2 and pi over 2. So we cannot look at those values, so you'll notice that there is no equality for these here because we're not including the endpoint. So we need to be even a little bit more careful with tangent than we are with the sine and the cosine on those endpoints. So we can see that since we have vertical asymptotes at negative pi over 2 and pi over 2, that's going to correspond to horizontal asymptotes. Once we look at the reciprocal, once we flip this through the origin here, not the reciprocal, once we look at the inverse, flipped through the origin here, it's going to correspond to horizontal asymptotes, and we can see that our inverse function now extends infinitely in both directions here, getting asymptotically close to negative pi over 2 and pi over 2, just like these get asymptotically close to negative pi over 2 and pi over 2 as vertical asymptotes. So some nice relationships here. I enjoy these pictures. So let's take a look at using these new restricted values to find each of these inverse trig functions here. So we just want to evaluate, and I'm almost always going to draw a picture for these guys here. So I want to find the cosine inverse of -1/2. What is sometimes good to do when we're learning these is to say, okay, I know that the inverse trig functions find me angles. So this is equal to some angle theta. And if I take the cosine of both sides here, I would get that -1 is equal to the cosine of theta. So what we're trying to find here is what angle would give me a cosine of -1/2. Well, let's draw a picture here. Here's my unit circle. I'm looking for where cosine is -1/2. Well, -1/2 is over here. This is fine. So remember that for cosine, we're looking at this restricted area up here, going from 0 to pi. So we're looking at the top half of the unit circle for cosine. And so where is it 1/2? That's right here. So that's going to correspond to this guy here. So I'm looking at this angle, and this is going to give me an angle theta of 2 pi over 3. So I'm just literally drawing my picture and using that to figure out what angle we must be looking at. And this angle here that we're looking at is 2 pi over 3. All right, we'll take a look at this next one here. We want the tangent inverse of the square root of 3. So tangents are a little bit trickier to solve just because we don't have that direct relationship, just finding the sine or the cosine, which corresponds to the side lengths there of this triangle that we're making in our unit circle, or the coordinates on the unit circle, however you're thinking about that. So this takes a little bit more work, but it's still possible. We're still looking for some angle theta, that when we take the tangent of theta, we get the square root of 3. So if I think about taking the tangent of both sides here, we would get that the square root of 3 is equal to the tangent of theta. So what we can do here, maybe if I write this the other way around, just to give myself a little bit more space here, I've got the tangent of theta equals the square root of 3. I'm trying to force in this ratio. I know that this is going to be the sine of theta over the cosine of theta. So if I could see that ratio on the right-hand side, that will be helpful to me. So what I'm going to do here to kind of force this in is write this over 1. So that still doesn't give me too much information, but if I had something like the square root of 3 over 2 or 1/2, that would give me some information, since those are the sines and the cosine values that I think that I should be looking for here. If there was a square root of 2, I might be thinking about square roots of 2 and looking at a 45-degree angle, but what I'm going to do here is multiply the top and bottom by 1/2, just as a creative way to get this to look how I want it. So now we're going to have the square root of 3 over 2 over 1/2. And if this is the sine of theta, and this is the cosine of theta, then this tells me I'm looking for some angle that has a sine of square root of 3 over 2. Oh, so since we're looking at the tangent, we need to restrict our domain. So we're going to be looking at negative pi over 2, but not including it, and then going up to pi over 2. This is our restricted domain for tangent. So we're looking for angles that live on this side of the unit circle. Since we're looking for a positive tangent, we know the tangent is positive in the first quadrant, so we can drop something in here. And this tells us that we're looking for, well, maybe I should try and draw this angle a little bit closer to where it is. I want the sine to be the square root of 3 over 2, and the cosine to be 1/2. So that's looking for this angle here, and this angle here is pi over 3. So here we're getting pi over 3 for our angle, inverse tangent of square root of 3. Also, if you have these values memorized, some people are better at memorizing than I am. I usually have to figure most things out because I have a terrible memory. But if you know that the tangent of theta, the tangent of pi over 3 is equal to the square root of 3, then you can just use that knowledge straight off and get your answer. Like I said, I don't have a lot of things memorized. I usually have to go figure out what things are, and that's okay. So there was me figuring it out. I'm just building in these halves so I can get the relationship directly in front of my face of some known value for sine and some known value for cosine, and I can make sure that all of those line up. I'm missing half my parenthesis here. Okay. All right, let's take a look at this last one, arctan of -1. Now, I do know what angle will give me a tangent of -1. So let's just kind of build that intuition here. We know that the arctangent is going to give me some angle theta. which tells me that if I take the tangent of both sides, I'm looking for some angle that the tangent is -1. And if I think about building my circle here, I know that I'm restricted to this side of the unit circle since I'm needing angles that go from -π/2 to π/2, not including those endpoints. I want this to be negative, so I'm going to be looking down here in this fourth quadrant where I know that the tangent is negative. And now I want -1, and the only way to get that would be to have something like the negative, let me write it over here maybe, having something like the -2 over 2 over the square root of 2 over 2. That would give me -1. I'm just trying to write that explicitly here if you don't have this value off the top of your head. This just says -1, and if this is my sine of theta over cosine of theta, then that tells me that this, if this is the point, square root of 2 over 2, negative square root of 2 over 2, then this is at negative, this angle is -π/4. So kind of squeezing it in over there, but this angle theta that we found is -π/4. So drawing pictures is your friend. For a lot of these, I'm just drawing a lot of unit circles and trying to map things in and see what lives where, and that is very helpful for me when I'm solving these. Okay, next we are going to use a calculator to find some approximate values here. Since our goal with these inverse, oh, I have this one listed twice here for some reason. Our goal with these inverse trig functions is to find an angle, and a lot of those times these ratios that we're going to have are not going to be these perfect trig values that are going to work out nicely. We're going to need to use a calculator to approximate here. So don't know how this one ended up on here twice, but we'll cross this guy out. But I want to find the sine inverse of 0.97. So this is not some value that we have off the top of our head, so we're just going to have to use a calculator here. But I think that what we can do is still try to use some intuition to see maybe we can try to approximate these values before we just put them into a calculator here. So that's what I'm going to do. So I'm just going to draw a unit circle here. And this is not crucial to the problem, but I do want to continue to build intuition here for this stuff. I'm looking for an angle, so this is going to give me some angle theta. So it's telling me I'm trying to find some angle theta whose sine is 0.97. And 0.97 is like way up here. It's super close to the top. The top there would just be a value of 1. So if I kind of map that off to the side here, this is going to be some like fairly obtuse angle. I would imagine that this is going to be something pretty close to 90 degrees, probably a little bit less, but I'm looking at some pretty extreme angle here. In fact, I would say that my picture is probably only giving me like 90%. It's probably a little bit higher, so we probably have some angle more like this. So I don't know. My guess is 80 degrees, something like that. That's just my guess before we plug it into a calculator. But that's all we have to do is just plug this into a calculator. We are asked to find both radians and degrees, so this is just practice in doing that. I'm just going to switch over to a calculator app here so that we can look at this. But what we want to do is find the sine inverse of 0.97. So we're going to just do this one at a time. Right now, you can see that my calculator is in radians. The little arrow is pointing at radians. Every calculator is different, so you're just going to have to get good with your calculator. Calculators are tools. You should be able to know how to use your tools. So yours might not be exactly like mine here. So make sure you're practicing, because when you get to an exam, the last thing you want is for your tools to fail you because you're not quite sure how they work. So the way that this calculator works is I put in my input value first, which is going to be 0.97, and then I'm going to hit the sine inverse button over here, and that's going to give me 1.33. We'll round to 2 decimal places here, and these are radians. Remember that my calculator here was in radians. So 1.33 will be my radian value. I just have that written down off to the side. We'll go put it on in a second here. Now let me switch my calculator to degrees, and we'll do the same thing here. Whoops. We'll do the same thing here in degrees. I'm going to put in 0.97 for my input, and then I want to look at the sine inverse, and now this is going to give me a different number, right? Because now we're in degrees instead of radians, so we wouldn't expect to get the right number. So here we have 75.93 degrees, which is pretty close to what I said. I mean, of course, I knew what this was going to be, but still, hopefully that argument makes sense, that we were looking for something that was going to be a little bit less than 90 degrees. So about 76 degrees is right there for us. So we'll switch back over to our picture now. Here we're getting that theta is equal to about, we don't want to say equal, but this is approximately 1.33 radians, which is the same as 75.93 degrees. So there we go. We have approximated using a calculator here for those values. Let's do the same thing for the cosine inverse of negative 0.4. So again, let's just see if we can't try to approximate what this value might be before we put it into a calculator. This is good. Oh, I should always draw the circle first. This is good because sometimes you might just make a boo-boo putting stuff into your calculator, and it's good to be able to catch that. Like, oh, I expected something closer to this. In fact, when I was going through these before I did this, I was doing that, and I was thinking about something slightly backwards, and I had to take a second and make it make sense to me. In fact, it might have been this exact one here. So I'm looking for a cosine value of negative 0.4. So that's going to be like around here, a little bit less than half on that side there. And so if I look at this angle, I know that half would give me 2 pi over 3. So that would be about 120 degrees, and I would expect this to be a little bit less since it's moved over a little bit less than 120 degrees. So there's my prediction. So now when we put this into the calculator, I'm thinking I should get something a little bit less than 120 degrees. So let's go back over to our calculator here. We're still in degrees, so let's just start with our degrees here. But I want to find the cosine inverse, so I'm going to put in negative. Where's the negative? I guess I maybe just use... Nope, it's over here. I want to use, oh, I need to do it last. Okay, 0.4 negative, and then I want to press the cosine inverse button. So that's there, and this is going to give me 113.58 degrees, which I said I think that it should be a little bit less than 120. So there we go. So I'll got that written off to the side here, and we'll put it on the screen once we go back over. But we want to get this in radians as well, so let me swap back to radians. You can see that over here the arrow is pointing at radian, so that means I'm in radian mode. And I'll do again 0.4, we'll make it negative, and then I'll press the cosine inverse button, and we'll get about 1.98 radians. So we'll switch back over here, and we now know that this angle theta that we are looking for is about 1.98 radians, which is about 113.58 degrees. So those were just kind of arbitrary questions. Here we're given a right triangle and asked to find this angle theta, which is, you know, more of an application that we might see as we want to use these inverse trig functions. So what we have here is we know something about the adjacent angle, and we know something about the hypotenuse here. So I know that the cosine of theta is going to be the adjacent angle 9 over the hypotenuse, which is 12. And this is 3 over 4, which is also 0.75. I'm just approximating because I want to do the same thing that I did before I go just put this into a calculator. Let's see if I can try and approximate what this value should be. So I'll draw a unit circle. I'm looking for where the cosine is about 0.75, which is about here. Remember that cosine, we're restricted to the top portion of the unit circle here, going from 0 to pi. And so we're looking at an angle here that is out here, and this is a little bit less than, I know that the square root of 2 over 2 is 0.7, so this is a little bit farther that way. So I would expect this to be a little bit less than 45 degrees. Since square root of 2 over 2, or 0.7, would correspond to this 45-degree angle here, I'm expecting, since it's shifted over to the right a little bit, that this will be a little bit less than 45 degrees. So let's go see if our intuition is right here. We'll go back to our calculator. We're in radians, so we'll start with radians here. So we should get something that's a little bit less than pi over 4, although maybe we don't know that approximation off the top of our heads. What am I looking for here? I want 3 over 4, which is 0.75. So I'll just type in 0.75. And I want to take the, which one was I doing? Cosine. Cosine inverse here. And we get a radian of 0.72. So we'll get that written off to the side here. Let's take a look at the degrees. So let's switch our calculator to degree mode. I'll put in 0.75, and I want to look at the cosine inverse. And there we go. In degrees, we get about 41.4. So yeah, like I said, it should, I think, be a little bit less than 45 degrees. And that is what we get. So we'll switch back here. So we get an angle theta is going to be about either 0.72 radians, or it will be about 41.41 degrees. So there we go. There is some applications of just using the calculator to get some of these angles in order to solve our problems. All right, now we're going to take a look at some these special relationships here when we're composing trigonometric functions with their own inverses. So again, I just stole something from our lecture on inverse functions here. And now we're putting this full definition to good use. So we might have seen that, yeah, if you compose f with f inverse of x, you just get x out the other side. Of course, it's just going to take x and it's going to map it to one spot and then it's going to map it right back to itself. And we see the same thing for the other direction here, that if we take f and compose it with its inverse, that yeah, f will send it over to some value and then f inverse will send it right back to itself. But we have the rest of the definition here, which says that this is only true for all x in the domain of, for this one says f inverse of x, which is our most inside function here. So remember, when we look at composition of functions, we start with the most inside function and we work our way out. So for this process to make any sense, our most inside function here, the f inverse of x, we need to be looking at x's in that domain. And same thing for the one below it. All of these input values need to be in the domain of our most inside function here, which is f, before we can apply f inverse after that. If x is not in the domain of f, then we are going to try and take f inverse of something that is undefined, which is not going to make any sense. So here we are looking at that and with things very carefully written out, that if we want to compose sine inverse with sine, if we want this relationship to be true, then x needs to be in the domain of sine inverse of x. So remember that sine inverse of x takes in ratios, and these ratios will be from -1 to 1, and it will give you an angle out the other side, and then we can take the sine of some angle once we find that value here. So same thing is true for the cosine. It takes in ratios from -1 to 1, and then for tangent inverse, since tangent has outputs going from -infinity to positive infinity, that means that tangent inverse has inputs also going from -infinity to positive infinity. So this is, I guess, about the best case scenario where you don't have to worry too much about the inputs here, since tangent inverse does take all real numbers in its domain, or has its domain. So now we are reversing things. So here we were putting an inverse function into a trig function. Here we're plugging a trig function into its inverse function. So now we're looking at the domain of the most inside function here. So this is the restricted domain for sine, which was -pi/2 to pi/2. The restricted domain for cosine, which is 0 to pi, and then the restricted domain for tangent, which is -pi/2 to pi/2, and here we're not including those endpoints, since there are vertical asymptotes there for the tangent function. So what this is telling us here is that if our x value lives in its domain, then yeah, the input is just the output. If it's not, then we're going to need to be a little bit more careful, and we'll see some examples of that going forward here. So let's take a look at evaluating the following. So we're going to take a look at our x input here, and our restricted domain for sine is from -pi/2 to pi/2. And here we can see that pi/3 is in this in this domain from -pi/2 to pi/2. if we want to see that more explicitly, I often need to see a picture to be totally convinced. I know that pi over 3 is an angle that looks about like that. I know that sine inverse is only defined on this side here, and this angle is on that side. So yeah, we're all good here. We don't need to do any sort of extra thinking. We just get this inverse property where the input is the output, since we are just plugging in something from a legit domain in for sine, and then we're going to take the sine inverse and send it right back where it came from. Let's take a look at this next one here. Here we're looking at an angle of 2 pi over 3. So is 2 pi over 3 in our restricted domain? Well, you can either just think about if it's true or not, but we know that 2 pi over 3 is this angle over here, which is not part of my restricted domain for sine. So we need to be a little bit more careful. This is not equal to 2 pi over 3. Sure would be nice if it was, but since we're restricting our domains, we do not get this. So what we can do is just kind of chase things through, and we'll just evaluate one portion at a time, just like we would have to do in any other sort of function composition. So let me move this a little out of the way. So what we get here is that the sine of 2 pi over 3, so I'm just going to straight evaluate what this is. What is the sine of 2 pi over 3? And it is the square root of 3 over 2, which corresponds to some value over here. So we could just be looking at the sine of this angle, which is something that we could do. But here I can just write that this is equal to the sine inverse of the square root of 3 over 2. Let me maybe move this out of the way. And so now I'm trying to find some angle theta that has a sine value of square root of 3 over 2, which is what I was referring to with this other angle over here, that this has a sine value of the square root of 3 over 2. And this angle here is an angle of pi over 3. So here we get pi over 3 as our solution. So not what our input was, but we had to kind of use some reference angle that was in our restricted domain for sine to find this. So here we did not get 2 pi over 3, but we got a related angle here. It's reference angle. All right, next one we've got cosine inverse of cosine of 2 pi over 3. So kind of just thinking, all right, is 2 pi over 3 in our restricted domain here? Remember that cosine is restricted to the top portion of the unit circle here, going from 0 to pi. 2 pi over 3 is this angle here. Yeah, that is totally in our restricted domain. So here there's no extra thinking to do, since 2 pi over 3 is in our restricted domain, the input is the output. The cosine inverse is just undoing the cosine, and we get 2 pi over 3 here. And then for this last one, we're looking for the cosine of negative pi over 3. So let's think about where that lives. Remember that for cosine, we need to be restricted to the top half of the unit circle here from 0 to pi. But unfortunately, negative pi over 3 is down here, which is not where we would like it to be. But we can just figure out what the cosine of negative pi over 3 is. So what are we looking at here? This looks like a value of 1/2. This is not my best 3. This is a value of 1/2. So now I can think of, where is cosine inverse of 1/2? What value in my restricted domain would give me a cosine value of 1/2? So if I think about that, we can think about this reference angle here coming down and hitting 1/2, and this is an angle of pi over 3. So a lot of pi over 3s on this page, not intentional. Not every answer is pi over 3, but here they happen to be. So there we go. We've got our solutions here to these ones. For the inputs that were part of our restricted domain, we can just use that the input is the output for these compositions of inverse functions. If the input is not part of our restricted domain, then we just need to evaluate one piece at a time and see where these things map to. All right, next we're going to look at composing trig functions with other inverse trig functions. So now we're not composing sine with inverse sine or cosine with inverse cosine, but we are composing inverse sine with cosine and sine with inverse cosine. So we'll need to be a little bit more careful here, but we can use things that we already know. So we're just going to evaluate maybe one piece at a time here for number 1. I think that I know what the cosine of 13 pi over 6 is. This seems to be a nice pi over 6 relationship here. So let me just draw a unit circle off to the side to give me something to look at. And we're thinking about 13 pi over 6. Well, I know if I go and make an entire revolution, that this will give me 12 pi over 6. 12 pi over 6 is 2 pi. And then I need to go one more pi over 6. So 13 pi over 6 is going to be this angle here. So 13 pi over 6 is coterminal. That's not my best pi. And this is coterminal with pi over 6. So I could say that this is going to be the same as the sine inverse of the cosine of pi over 6, just to get things looking a little bit nicer here. I know that the cosine of pi over 6 is going to be the square root of 3 over 2. So now we're looking at the sine inverse of the square root of 3 over 2. So we are done thinking about cosine. The cosine is out of the problem at this point, and now we're looking for what angle theta is going to give me a sine value of the square root of 3 over 2. So I could say that what this is saying is the sine of what angle theta is the square root of 3 over 2. And if I want to put that over here, maybe I switch colors. If I'm looking for this value here, I know square root of 3 over 2 is up here, which means that I'm looking at this angle here, which is pi over 3. So here we will get that theta is again equal to pi over 3. Like I said, it's not always pi over 3, but that just seems to be appearing a lot in our answers here. I don't think that we'll see that in the next one here, because if I'm trying to tackle this one, the thing that we want to do first is see what angle is going to give me this relationship of -3 over 7. And that's just not something that I know off the top of my head. So we're going to need to get a little bit more creative here. So what I'm going to do is just draw my unit circle like I have been doing. And I can use this to get some relationships here. I know since I'm looking at cosine inverse that we're going to be restricted to the top half of the unit circle here. And I'm looking for a ratio of -3 over 7. So since we're negative, I know that cosine's negative over here in this quadrant. All students, or a smart trig class, only sine is positive in the second quadrant. So that'll tell me if I drop in a right triangle here, that this value will be -3, and I have a hypotenuse of 7. Since I'm looking at a cosine, I'm really looking at this angle, but I'm thinking about its reference angle here. So theta is the obtuse angle, its reference angle is theta prime there. The cosine inverse is what we are looking for. So remember that cosine inverse of -3 over 7 should just be giving us some angle here. And so this is the angle theta that I've drawn in over here. This is just a nice relationship to help get us where we want to go. And now if I draw this picture, we're missing a side over here. Maybe I call this side length A or something, or maybe we'll call it Y, since this is traditionally what we call Y. Let's figure out what this value is so that we can use it. Because now I want to find the sine of this angle theta. Maybe I could color code a little bit. I'm looking for this angle theta, which is the same as this angle theta, because all of this was just theta. So I'm just making some substitutions here. So I'm now looking for the sine of theta, which will be the same as the sine of theta prime here. So here I'm looking for the opposite, which is y, over the adjacent over the hypotenuse, which is 7. So let's go figure out what y is using the Pythagorean theorem. We should be getting that y squared plus -3 squared is equal to 7 squared. So we'll get that y squared is equal to 49 minus 9, so that y is equal to plus or minus the square root of 40. Y is equal to plus or minus 2 square roots of 10. And now we need to figure out, do we need the plus or the minus version? And since the sign is positive in this quadrant, we want the positive version. So y is equal to the positive 2 square roots of 10. So now we've got it, that the, whoops, that's not what I'm trying to write. that the sine of theta, which happens to be the cosine inverse of -3/7, is equal to y over 7. We now know that y is 2 over the square root of 10, and we know that 7 is 7. So there we go. Here is the sine of the cosine inverse of -3/7. So building our right triangle here, looking at a reference angle, using the Pythagorean to solve for the missing side, will get us what we want. So there we go. We have composed some trig functions with the inverses of other trig functions. All right, now we're going to look at writing a trigonometric expression as an algebraic expression. And this is a skill that comes in very handy in calculus when you're trying to figure some problems out, of being able to draw in a right triangle quickly and get relationships of sides in terms of other sides from their trigonometric relationships. So for this first one here, we're asked to find a simplified expression for the cosine of the sine inverse of x over 3. Did I not delete it? Oh, okay, I meant to split these apart on 2 separate pages. So we'll see number 2 on the next page, because we might need more room. So we are trying to figure out what's going on here. So let me draw a unit circle. Let me change colors back to yellow. So there's different approaches that we can take for these. For this one, I'm drawing a unit circle in. And I am thinking about... we're talking about the sine inverse, so I know that we're going to be restricted to the right half of the circle here. So that's talking about the sine inverse. And then we're going to talk about the cosine, so I know that I'm going to be restricted to the top half here, which shows me that we should be focused on this first quadrant, where these two restricted domains intersect. So I'm going to just drop in some random angle here in the first quadrant, since I know that that must be where we are living here. Okay, so let me drop in a right triangle, like so. And now, let's get this thing labeled. I know that since this is a unit circle, that this radius here will be 1. And I'm looking for some angle that will give us a sine of x over 3. So that means that this side over here is x over 3. The sine corresponds to this height, and that's going to be x over 3. Okay, so now we've got this thing set up. Just a note about this relationship here. Remember that the input for sine inverse has to be between -1 and 1. So that is why our domain here needs to be between -3 and +3. If you think about plugging those in, -3 is the smallest number we could plug in, because that would give us -1. And then if we plugged in 3, that would give us a +1. So that's the largest value we would be able to plug in here. So just a quick note about that domain there. Okay, now we're trying to figure out what the cosine of this is. So what we would like to find, the cosine, is going to be this side of our unit circle here. So this is what we're trying to find. We're just going to use the Pythagorean identity to solve this guy here. So we've got the cosine squared of theta plus the sine squared of theta, which in this case is x over 3 squared, should be equal to 1. So we will use this relationship to solve for the cosine of this angle theta, and that will give it to us here. So if I subtract the purple from both sides, we'll get x squared over 9. If I get a common denominator on the right-hand side, I will get 9 minus x squared over 9. Ignoring this for right now, we're going to see this one on the next page. I just forgot to delete it. We'll take the square root of both sides. We'll get that the cosine squared of theta is equal to the square root of 9 minus x squared all over 9, plus or minus. And then, oh, I didn't mean to write my squared there. I've taken the square root now, so I just have the cosine on the left-hand side is equal to plus or minus the square root of 9 minus x squared over 9. I can actually take the square root of the bottom portion there. Well, the cosine of theta is equal to plus or minus the square root of 9 minus x squared all over 9. And now we need to decide if we want the positive or the negative version here. Since we're in the first quadrant, we know that the cosine is positive, so we want the positive 9 minus x squared. Whoops, this should have been a 3. We took the square root of the numerator and the denominator, and we got the 3 there. So a little typo. This is square root, and that's over 3. And this is what we are looking for. So this is the cosine of the sine inverse of x over 3. So there we go. We have turned this trig expression into an algebraic expression. So in calculus, we could then go use this algebraic expression to take an integral or derivative or whatever we want to do from there. Okay, taking a look at this example here, we want to find a simplified expression for tangent of sine inverse of this funky expression here for this domain x bigger than 4. So what we are going to do in this one is not draw a unit circle, but just try and use some relationship here. So we've got that we want to find sine inverse of x squared minus 16 over x. We know that this is just going to be some angle theta. And if I take the sine of both sides here, we would get that the square root, let me write it maybe the other way, that sine of theta is equal to the square root of x squared minus 16 over x. So that's just using the inverse relationship there. And I also know that the sine is this ratio of the opposite over the hypotenuse. So we're just going to drop in a right triangle here. So not a unit circle, but just a right triangle here. And I know that if this is the angle theta that we are interested in looking at, then the opposite is going to be the square root of x squared minus 16, and the hypotenuse is going to be x. And then we can use the Pythagorean theorem to figure out what this other side is. Maybe we call it a. Normally we might call that the x side, but there's already x's in here, so let me just give it a different name that's not x or y, so we'll call it a. But I know that a squared plus the square root of x squared minus 16 squared should be equal to x squared. And if I solve this for a, we'll get that a squared plus x squared minus 16 equals x squared. If I get everything that's not an a on one side, we'll see that a squared is equal to 16. So a is equal to 4. So I'll put a little bubble around that, and that will be important to us here. So here, this angle theta, we get this right triangle relationship here. And what we want to find is the tangent of theta. Remember theta, if I switch colors here, theta is equal to all of this, all of this, all of this. So I'm just plugging in this gross inverse sine function, but I'm just calling it theta now instead. Because it's nice, we can just look at this triangle. We're still just talking about this theta here, and I want the tangent, which is going to be the opposite, TOA, opposite over the adjacent. So the opposite is still the square root of x squared minus 16 all over 4. So this is the tangent of theta, and theta was just our renaming of the sine inverse of the square root of x squared minus 16 over x. So there we go. And again, this is a nice relationship that you could get. So if you need to go do some calculus with this, we have an algebraic expression instead of a bunch of trigs being composed together. So there we go. Here is writing trig expressions as algebraic expressions. All right, that takes us to the end of this one, and it's time to practice. So good luck with the homework. Please let me know if you have any questions. I'm always happy to help, and I'll see you in our next video.